Hello, everyone, and welcome to our deep dive into one of the most transformative technologies in modern artificial intelligence, convolutional neural networks, or CNNs. This presentation is titled The CNN Revolution, a guided tour of architectural innovation, and we aim to trace the history of CNNs, starting from their surprising origins in biology all the way to their deployment in state-of-the-art computer vision systems today. CNNs are the backbone of virtually every modern image recognition application, from self-driving cars to medical diagnostics. The imagery on this slide perfectly captures the journey we are about to undertake, moving from the intricate branching structure of biological neurons, which serve as our inspiration, to the engineered complexity of the digital circuit board, which executes the algorithms. We will explore the fundamental building blocks, understand why they are so effective, and review the landmark architectural breakthroughs that pushed error rates past human performance levels. Prepare to navigate the core concepts that define how machines learn to see the world. Let's get started on this tour. To appreciate the solution that CNNs offer, we must first understand the challenge. Why is vision so incredibly hard for computers? For us, seeing a golden retriever puppy, as shown on the left, is trivial and immediate. It happens subconsciously. Our human perception is intuitive and rich. We don't see raw sensory input. We see high-level features like fur texture, ears, and puppy face. However, when a computer looks at the same image, as shown on the right, it sees nothing but a massive grid of pixels. In fact, for a standard high-definition image, this grid could contain millions of individual data points. The zoomed-in section reveals that the puppy is just a collection of numerical values representing the intensity or color of light at that precise location. These raw numbers lack any inherent meaning or structure. Traditional AI methods struggled immensely because they attempted to process this enormous, flat grid of data without the hierarchical feature processing that our brains perform. This inability to group meaningless pixels into meaningful patterns, like edges, shapes, and eventually, a puppy, was the monumental challenge. The core question we must address is this: how can we teach machines to see the world not as millions of isolated pixels, but as a hierarchy of meaningful, complex patterns, just like we do? The breakthrough in computer vision didn't come from computer science initially. It came from neuroscience. The true blueprint for the convolutional neural network lies in the organization of the mammalian visual cortex. In the 1950s, scientists David Hubel and Torsten Wiesel conducted seminal experiments with cats, which revealed two key principles that directly inspired CNN architecture. The first principle is ** local receptive fields **. Individual neurons in the visual cortex do not look at the entire visual field. Rather, they respond only to stimuli within a small, specific region, their local receptive field. The second, and perhaps most critical, principle is hierarchical structure **. These local field neurons are organized in layers. Lower-level neurons respond to very simple, fundamental patterns, such as oriented lines and edges. These then feed into higher-level neurons, which respond to increasingly complex combinations of those simple patterns, eventually recognizing things like corners, shapes, and complex objects. The diagram on the right illustrates this perfectly. Simple lines detected in Layer 1 combine in Layer 2 to form corners and T-shapes, which in turn combine in Layer 3 to form a complex cross shape. This architecture is incredibly efficient because it allows us to detect complex patterns anywhere in the visual field using the same underlying detectors. This biological concept formed the direct inspiration for early networks like the neocognitron in 1980 and, ultimately, modern CNNs. When designing a system to process images, why not simply use a standard fully connected network, or FNN? The answer is shown here. Scalability is the immediate killer. If you consider a modest 100 by 100 pixel grayscale image, that's 10,000 input pixels. If the first hidden layer had just 1,000 neurons, you would immediately require 10 million connections, or parameters. This is computationally intractable for modern, high-resolution images, and it also leads to massive overfitting. The convolutional neural network provides a brilliant solution, built upon two core insights derived from the visual cortex. First is *** partial connectivity. Unlike FNN neurons, which connect to every pixel, CNN neurons connect only to pixels within their small, local receptive field. This drastically reduces the parameter count. Second, and even more vital, is * weight sharing ***. Instead of learning unique weights for every neuron, a small set of weights, called a filter or kernel, typically 3x3 or 5x5, is slid or convolved across the entire input image. This single filter, containing just a few parameters, 9 parameters for a 3x3 filter, is shared by all neurons in a given output feature map. This clever trick means the network can detect the same feature, say a vertical edge, whether it appears in the top left or bottom right of the image, without having to learn that feature multiple times. This property is known as translation invariance, and it makes CNNs efficient, scalable, and inherently suited for image data. The operation of sliding a filter across an image is known as convolution, and it's controlled by two main hyperparameters, the stride and padding. In Part 1, we see the function of the filter and the resulting feature map. Each filter acts as a specialized feature detector, which the CNN learns automatically during training. When our vertical line detector filter is applied to the input image, it produces a high activation value only in the region where the vertical line is detected. The resulting 2D output, the feature map, visually highlights exactly where this feature exists. Now let's look at two practical considerations. In Part 2, we introduce *stride**, which is the step size the filter takes as it moves across the input. A stride of 1 means the filter moves 1 pixel at a time, resulting in a feature map that is only slightly smaller than the input. However, using a stride greater than 1, say a stride of 2, significantly downsamples the feature map, reducing its spatial dimensions by half in this example, and consequently cutting computational cost. This is a common method for reducing dimensionality. In Part 3, we look at **padding**, which involves adding zeros around the border of the input. If we use valid padding, which means no padding, the output feature map is always smaller than the input. If we use same padding, we add enough zeros to the border so that the output dimensions remain exactly the same as the input dimensions. This is especially useful for preserving spatial information as the image passes through deeper layers of the network. While convolutional layers extract features, the pooling layer serves a crucial role in managing the network's representation size. The primary goal of pooling is to progressively reduce the spatial dimensions, which simultaneously reduces computational load, saves memory, and decreases the total number of parameters, acting as a crucial defense against overfitting. Pooling layers don't have weights themselves. Instead, they aggregate features within their receptive field using a simple function. The most common type, and the one we show here, is *max pooling ***. Using a 2x2 filter with a stride of 2, max pooling simply outputs the maximum value found within that 2x2 region. As you can see in the example, the input region containing 2, 8, 4, and 6 yields 8 in the output map, preserving the strongest feature activation while throwing away 3 other values. The key benefit this provides is *invariance**. Because we summarize a region with a single value, max pooling creates a degree of robustness to small translations, rotations, and scaling. The exact position of a feature is now less important. Look at the translation invariance example at the bottom. Scenario A and Scenario B are slightly shifted versions of the same input, but after 2x2 max pooling, the resulting 3x3 output maps are identical. This makes the network far more reliable and robust in the face of minor image variations. Now that we have covered the 3 foundational building blocks, convolution, activation, ReLU is typically used, and pooling, we can look at how they're stacked together to form a typical CNN architecture. The standard architecture involves repeating stacks of CONV ReLU pool blocks. As an image progresses through the network, 2 important structural changes occur simultaneously. First, the spatial dimensions, the height and width, shrink primarily due to the pooling layers. For instance, the input starts at 28x28, but after the first block, it is reduced to 13x13. Second, the network's depth, meaning the number of feature maps or channels, grows. The network starts with just one input channel, but by the end of the first block, it has 64 feature maps and later 128. This growing depth allows the network to learn increasingly complex combinations of features. The entire stack of convolutional and pooling layers acts as a powerful, hierarchical feature extractor. Once these rich, high-level features have been extracted, the feature maps are flattened into a single vector, and this vector is then fed into a standard fully connected FC network for final classification. The Python code snippet below demonstrates how simple this architecture is to define, stacking multiple convolutional blocks, flattening the output, and finishing with standard linear layers for prediction. This fundamental pattern has driven computer vision success for decades. While the theoretical building blocks of CNNs existed for years, the true revolution, the period of staggering innovation, was driven almost entirely by the annual ImageNet Large-Scale Visual Recognition Challenge, or ILSVRC, which began in 2010. This competition became the proving ground for computer vision breakthroughs. The goal was massive: classify 1.2 million images into 1,000 distinct classes. The metric used to track progress was the top 5 error rate, which is the percentage of images where the correct label was not included in the model's top 5 predictions. The progress was nothing short of staggering, as demonstrated by the plummeting red line on this chart. In 2011, the pre-AlexNet models hovered near a 26% top 5 error rate. Then, in 2012, AlexNet halved that error rate. Subsequent architectures continued to push the boundaries, reducing the error rate year after year, until ResNet in 2015 achieved 3.6%, significantly surpassing the estimated human performance threshold of 5%. This era, from 2012 to 2017, saw the introduction of landmark architectures that we are about to tour, each solving a specific computational or gradient problem and collectively defining the state of the art. Our historical tour begins not with the ImageNet explosion, but with the foundation, LeNet 5, developed by Yann LeCun and his colleagues in 1998. The big idea behind LeNet 5 was simple yet profound. It was the first widely successful commercial application of CNNs, proving that these networks were viable for real-world deployment. Its key application was recognizing handwritten digits on checks used by banks, a task it performed with high reliability. Architecturally, LeNet 5 established the fundamental, elegant pattern for future CNNs: a simple stack of convolutional layers, followed by average pooling, and culminating in fully connected layers for classification. However, looking at the diagram, we can see crucial differences compared to modern CNNs. Firstly, LeNet 5 used the tan activation function, which is prone to the vanishing gradient problem and trains much slower than modern techniques. Secondly, it used average pooling, which is generally less effective at preserving the strongest feature activation than max pooling, which is now the dominant choice. Finally, the output layer used an RBF, radial basis function, instead of the softmax function used today for probability distributions. Despite these differences, LeNet 5 provided the essential blueprint, but it took the availability of powerful GPUs and large datasets over a decade later for the deep learning revolution to truly ignite. The true inflection point in computer vision history arrived in 2012 with AlexNet, developed by Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton. Their big idea was to prove that truly deep CNNs, trained efficiently on GPUs using newly available large datasets like ImageNet, could achieve breakthrough performance. The results were stunning. AlexNet won the 2012 ILSVRC competition with a massive 17% top 5 error rate, which effectively halved the performance error of the previous year's winner. This single moment convinced the entire academic and industrial world that deep learning was the future of computer vision. AlexNet introduced several key architectural advances. First, it was significantly deeper and wider than LeNet 5. Crucially, it was the first to successfully stack multiple convolutional layers directly on top of each other, building complex feature hierarchies. Second, and perhaps its most enduring legacy, was the use of the *ReLU activation ** function, the rectified linear unit, which solved the vanishing gradient problem inherent in tan and sigmoid functions, enabling the network to train much faster. Third, To combat overfitting in its massive, fully connected layers, it popularized **dropout**, a novel regularization technique that randomly shuts off neurons during training. Finally, it utilized aggressive data augmentation, artificially increasing the training set size by shifting, flipping, and changing lighting in images, which forced the model to generalize much better. AlexNet was the spark that started the revolution. 2 years after AlexNet, GoogLeNet appeared, tackling a fundamental new constraint: how to go deeper without sacrificing computational efficiency. The big idea was to go deeper, achieving higher accuracy, but to do it more efficiently through the **Inception Module **. GoogLeNet won the 2014 ILS-VRC with a top 5 error rate below 7%, but its staggering achievement was its efficiency. It had 10 times fewer parameters than AlexNet, boasting only 6 million parameters compared to AlexNet's 60 million. The Inception module, shown in the diagram, is a network-in-a-network block that processes the input in parallel. It achieves multi-scale processing asterisk by using multiple different kernel sizes, 1x1, 3x3, and 5x5, simultaneously on the same input, allowing the layer to capture features at different spatial scales. Critically, to maintain efficiency, GoogLeNet cleverly utilized *1x1 convolutions as bottlenecks ***. Before the expensive 3x3 and 5x5 convolutions, a 1x1 convolution is used to aggressively reduce the channel depth. This drastically cuts the computational cost without losing much information. Finally, the outputs from all these parallel paths are stacked together via depth concatenation asterisk to form a single, deep feature map that captures rich, multi-scale information. This focus on parallelization and efficiency marked a major shift in CNN design philosophy. The year 2015 brought us ResNet, perhaps the most critical architectural innovation since AlexNet. Developed by Kaiming-He et al., the big idea was to enable the training of extremely deep networks, up to 152 layers, using residual learning via skip connections ResNet won the 2015 ILS-VRC with a staggering 3.6% error rate, crossing the human performance threshold. The fundamental challenge ResNet solved was the asterisk degradation problem. Simply stacking more layers deeper into the network surprisingly led to training accuracy getting worse, not better. This wasn't overfitting. It was the difficulty of optimizing extremely deep networks due to vanishing or exploding gradients. The solution is elegant: the skip connection, also known as a shortcut connection. In a plain block, the layer learns the direct mapping h(x = f(x). In a residual block, the input x is added directly to the output of the block f(x). Thus, the layer is now forced to learn the asterisk residual f(x) = h(x) mathematically. It is far easier for a stacked layer to learn to output 0, effectively allowing the input x to pass through unchanged, than it is for it to learn a complex identity mapping h(x = x directly. This allows the network to effectively skip layers that aren't useful, creating a clear, unimpeded gradient path through hundreds of layers, finally solving the depth problem. Following the landmark achievements of AlexNet, GoogLeNet, and ResNet, the field of computer vision experienced what we might call an architectural Cambrian explosion. Researchers rapidly diversified and refined these core ideas, focusing heavily on efficiency, feature reuse, and better gradient flow. 4 key innovations define this era of refinement. First, **Exception**, which moved beyond the Inception module by completely replacing it with depthwise separable convolutions **. This method assumes that spatial patterns and cross-channel correlations can be modeled separately, resulting in massively parameter-efficient models that are often lighter and faster than their predecessors. Second, *DenseNet took the idea of feature reuse to its extreme. Within its dense blocks, every layer receives the feature maps of all preceding layers as input, promoting maximal information flow, mitigating the vanishing gradient problem further, and requiring fewer parameters overall. Third, *CNet introduced squeeze and excitation blocks, a form of feature recalibration. These blocks learn to assess the importance of each feature channel, allowing the network to turn up the relevant channels and turn down the less important ones, improving overall feature representation quality. Finally, *efficient net * introduced a principled approach called ** compound scaling *. Instead of arbitrarily scaling a network's depth, width, or input resolution, compound scaling optimizes these three dimensions simultaneously using a fixed set of coefficients, achieving state-of-the-art accuracy with unprecedented efficiency. For the machine learning practitioner, choosing the right architecture is often not about picking the single best model, but rather balancing critical trade-offs based on project constraints. This chart illustrates the crucial ** accuracy versus efficiency trade-off **. We generally measure three key dimensions when selecting a model. First, *accuracy. How well does the model perform on a standard benchmark like ImageNet? Second, model size *. How many parameters does it have? This is crucial for deployment on edge devices like mobile phones or embedded systems where memory is limited. Third, *inference speed / compute *. How many floating point operations, or GFLOPs, are required per image? This determines deployment latency. The scatter plot shows various models plotted against accuracy, y-axis, and parameters, x-axis. The ideal model sits high and left on this graph. High accuracy, low parameter count. The curved line, labeled the ** efficiency frontier *, represents the best possible performance for a given computational budget. You can see older models like ResNet 50 and Inception v3 sitting below this frontier. Modern architectures, such as EfficientNet v2 and ConvNeXT, have successfully pushed this frontier outward, offering significantly higher accuracy for the exact same parameter count or computational budget, giving practitioners powerful tools tailored to specific resource limitations. Moving into the practical side of CNN application, we confront a reality. Training a state-of-the-art CNN from scratch is incredibly resource-intensive, requiring massive datasets and computational power that most users simply don't have. This is where transfer learning * becomes the single most effective strategy in the practitioner's playbook. The core insight is that features learned by a CNN are hierarchical and highly reusable. The lower layers * of the network, as we discussed, learn generic features like simple edges, corners, and textures, features that are common to virtually all images, regardless of the task. The higher layers * learn more task-specific features, such as dog snout or car wheel. The transfer learning strategy, illustrated in the process flow, takes advantage of this. We start with a model pre-trained on a massive dataset, typically ImageNet. We then freeze the lower convolutional layers, which act as the reusable, generic feature extractor, protecting those valuable learned weights. We remove the model's original classification head, which was only designed for ImageNet classes, and add a new, custom head * tailored to our specific task, e.g., classifying flowers or recognizing defects. Finally, we * train only the weights of this new head * on our smaller, custom dataset. By starting with a highly capable feature extractor, we achieve high performance quickly and efficiently, even with limited data. Let's translate the abstract concept of transfer learning into concrete code steps, using a hypothetical but common scenario. Fine-tuning a pre-trained ConvNeXT model for the Flowers 102 dataset, which is challenging because it contains only 10 training images per class. Step 1 is to load a pre-trained model **. Using frameworks like PyTorch and TorchVision, we can easily access state-of-the-art models along with weights pre-trained on ImageNet. The key here is passing the weights equals weights argument during model initialization. Step 2 is to replace the classification head **. The original ConvNeXT model has a final linear layer designed to output 1,000 values for ImageNet classes. We replace this layer with a new linear layer built for our specific task, in this case, 102 flower classes. We target the specific index of the classification layer, model, classifier 2, and instantiate a new linear layer with the correct output size. Step 3, which is critical for protecting the model, is to freeze the base layers **. We iterate through the parameters of the feature extractor, model features, and set their requires grad property to false. This prevents their weights from being updated by the large initial gradients, ensuring the valuable generic features are preserved. After training only the new head for a few epochs, the final step involves unfreezing all layers and running a final, gentle fine-tuning phase with a very small learning rate, which allows the generic features to subtly adapt to the specific custom data. This approach is the gold standard, achieving high accuracy where training from scratch would fail entirely. While classification, answering the question of what is in this image, was the initial focus of CNNs, many real-world applications require more granular understanding. We must extend the capability to answer, where are the objects? We move from classification to two related yet distinct tasks. First, classification and localization asterisk. Here, the task is to identify a single dominant object and draw a precise bounding box around it. This is typically implemented by adding a second head to the CNN output, alongside the standard classification head. This new head is a regression head that predicts 4 numbers, the bounding box coordinates x, y, width, and height. Training requires a combined loss function, pairing the standard cross-entropy loss for classification with a spatial loss, often a variant of the intersection over union or IOU loss for the bounding box regression. The second, more complex task is asterisk object detection asterisk asterisk. The goal here is to detect and localize all objects of interest in the image, often resulting in multiple boxes and multiple labels, as seen on the right. This is a much greater challenge because it requires the network to propose and evaluate many potential object locations simultaneously, which demands highly efficient and sophisticated architectures, leading us to our next topic. Early object detection methods relied on running a classification network repeatedly across many different sliding windows, which was excruciatingly slow. The You Only Look Once, or YOLO paradigm revolutionized this field by shifting the strategy. Instead of running a classifier many times, it looks at the image only once to generate all predictions simultaneously. The key enabling idea for YOLO is the asterisk fully convolutional network, or FCN asterisk. In FCNs, the dense, fully connected layers at the end of a traditional CNN are replaced with equivalent convolutional layers. This transformation achieves 3 critical advantages. First, the FCN can now accept inputs of any size, not just fixed dimensions like 224 x 224. Second, for a larger input image, the FCN produces a correspondingly larger grid of outputs, all in one pass. Third, each cell in this output grid corresponds to a specific region in the input image and contains a full set of predictions, including class probabilities, bounding box coordinates, and an objectness score, indicating the likelihood that an object is present. Because the FCN produces many redundant or overlapping detections for the same object, a crucial asterisk post-processing asterisk step called asterisk non-max suppression, NMS, is required. NMS cleans up the output by discarding boxes with low objectness scores and removing overlapping boxes for the same object, keeping only the single prediction with the highest confidence. Pushing the boundaries of computer vision even further, semantic segmentation ** aims for pixel-perfect understanding. The ultimate goal is to classify every single pixel in an image, assigning it to a specific class label, such as road, car, or building. This creates a segmentation mask where all objects of the same class are merged together. This task is crucial for applications like autonomous driving, where knowing the precise boundaries of objects is essential. The challenge here is that standard CNNs, because they rely on pooling layers, are specifically designed to shrink spatial dimensions, throwing away the precise pixel-level information needed for segmentation boundaries. The solution is the Encoder-Decoder architecture popularized by structures like UNet. This architecture is V-shaped, as shown in the diagram. The encoder usually a standard pre-trained CNN like ResNet, downsamples the input to extract high-level, rich semantic features, focusing on what is in the image. The decoder then uses a series of upsampling layers, such as transposed convolutions, to gradually increase the resolution back toward the original size. The crucial innovation is the use of *skip connections ***. These connections carry fine-grained spatial detail directly from corresponding encoder layers to the decoder layers. By combining the high-level semantic meaning from the bottleneck with the low-level spatial detail from the skip connections, the network can recover sharp, accurate boundaries, achieving pixel-perfect classification. While CNNs remain a dominant force and continue to evolve, the field of computer vision is expanding rapidly, focusing on even more complex and nuanced challenges that move beyond simple detection and segmentation. We are currently witnessing exciting developments across several frontiers. First, vision transformers, or ViTs*. These are an alternative architecture that treats an image as a sequence of patches, leveraging the powerful self-attention mechanisms originally developed for natural language processing. ViTs are now challenging CNNs for state-of-the-art performance, especially with massive datasets. Second, image generation and multimodality ***. Models like DALLE and Stable Diffusion create hyperrealistic images from simple text prompts, demonstrating models that understand and synthesize both text and image data together. Third, **explainability, XAI. As deep learning models become critical in fields like medicine and finance, we need to move beyond black box predictions. XAI techniques generate visualizations, often heat maps, to show which parts of the image contributed to the network's final decision, critical for trust, auditability, and debugging. Fourth, **adversarial robustness**. This research focuses on making models resistant to tiny, imperceptible perturbations in images, often called adversarial examples, which are designed specifically to fool the network into making incorrect high-confidence predictions. Finally, few-shot learning * tackles data scarcity. This mimics human learning by training models to recognize new object classes from just one or a handful of examples, reducing the massive data requirements typically associated with deep learning. We have now completed our guided tour of the CNN revolution, tracing its lineage from biological inspiration to the bleeding edge of computer vision. Let's summarize the core principles and practical takeaways that drive this field. First, the asterisk power of hierarchy ***. CNNs succeed because they mimic the visual cortex, building complex features from simple edges in a structured, hierarchical manner. Second, the *** efficiency of convolution ***. Weight sharing and local connectivity make CNNs computationally feasible for massive image datasets, while providing the crucial advantage of translation invariance. Third, the legacy of innovation ***, the Ascent era. A rapid series of architectural breakthroughs, from AlexNet's depth to GoogLeNet's efficiency and ResNet skip connections, solved key challenges and pushed performance beyond human levels. Fourth, the practitioner's edge ***. The most important practical takeaway is this: you rarely need to reinvent the wheel. Transfer learning * with pre-trained models is the single most effective, high-performance strategy for building custom vision applications efficiently. Finally, the expanding horizon ***. The core CNN principles are robust and are constantly being extended to solve an ever-widening range of tasks beyond simple classification, including complex localization, real-time object detection with YOLO, and pixel-level semantic segmentation. Thank you for joining me on this tour of architectural innovation.